Okay, let's solve the next example. Okay, in this example, a mass spring damper system is given to you where basically the spring is a nonlinear spring. Okay, then they have given you the equation for that spring. Okay, and the inputs of the system is the applied force here. Okay, and basically they want you to first model the system. Okay, and then break it down to state space equations, okay, or state equations. So for this problem, since this is super easy, yes, I'm gonna neglect all these steps to derive the model. I'm gonna leave it to you guys to derive this model, okay? And then if you go ahead and apply the nonlinear spring to this model, okay, you'll see that the dynamics of the system is mz double dot plus bz dot plus kz or k1 z plus k3 zq equals to the applied force, or capital F sub a, as a function of time. Okay, and clearly this system is nonlinear because you have z cube here, yes? And we're gonna model this system. Okay, sorry, we're gonna put the system into the state equations. Okay, I'm gonna go with my 4 steps, just like the previous example. Step 1, I'm gonna comment on the number of states and on the number of inputs. Okay, so I'm gonna determine the order and the number of inputs. Basically, your order is the number of states or the number of first order differential equations that you're looking for, and inputs are exactly given to you, like directly given to you. Sorry. Okay. So n is the order of the system. N is in fact the maximum order derivative that you have here. You have second order derivative. Okay. So n is equal to 2. And R is the number of inputs. In this problem, you have only one input, and that's the applied force. Okay. Now I'm going to go to step 2. In step 2, I'm going to set up my state and input variables. Okay, so set up your state and input variables. Okay, so look, I have 2 states here because the order of the system is 2. Okay, so I would have x1 and x2. I need to figure out what they are. Okay, and then my input is only one input. I'm just going to give it as u. Now, okay, let's go and determine the states. For this system, I need the order of the system is 2. I need 2 states. I look at the maximum order derivative here, and I would go 1 order derivative below that maximum order. So my first state would be z, and my second state would be z dot. You see that? Z dot is exactly 1 order derivative below that maximum order z double dot. And my input is in fact applied force, yes? And I'm gonna put it as capital F sub A T. This is force that's applied on the system. As easy as this. I'm gonna go to step 3, which is basically writing down the n as equal to 2 number of first order differential equations. Yes, so I'm gonna write down 2, or n equal to 2, sorry, first order differential equations. Okay, so look at this. I'm going to copy again. I'm going to copy the equations for the states. So I'm going to copy these guys and I'm going to paste them here. And I'm going to take the derivatives. Anytime the maximum order derivative happens to be on the right hand side, I would isolate it from the dynamics of the system and I would bring it here. Yes? So let's go ahead and do that. X1 dot equals to Z dot. Z dot is not the maximum order derivative. I'm okay here. X2 dot equals to Z double dot. Look, Z double dot in your dynamics is the maximum order derivative. So isolate this guy from the dynamics of the system and bring it down below. Yes? So for this problem, this is going to be 1 over m negative b z dot negative k1 z negative k3 zq. Yes? Plus f sub a. Okay? So what I did was I just isolated z double dot from the dynamics of the system and brought it here. Now I can go to step 4. In step 4, basically you're going to rewrite the equations and substitute basically z with x1, all the things that you had in step 2. Z dot with x2 and f sub a with u. Okay, so let me go ahead and copy these equations from here. I'm going to copy them and I'm going to paste them here. And in these equations, what I'm going to do is I'm going to first go ahead and any z that I have, I'm going to substitute them with x1. So this is going to be x1. This is going to be x1. Okay. Any z dot that I have here, I'm going to substitute them with x2. So z dot here, it's going to be x2. And z dot here, it's going to be x2. And that's it, I think, yes. Now, the last thing that I need to take care of it is f sub a. I need to substitute it with u. Okay, so I have it only here. And I'm going to substitute this one with u. Look at this. At this point, I do not need z double dot anymore. I get rid of that one because I substituted that one, yes? So I bring these terms a little bit to the left to just make it a little bit nicer. Okay, and this is your state equations, okay, your state variable equations. Again, guys, note that on the right hand side and on the left hand side, okay, you have specific components. On the right hand side, you have only x1, x2, and u. There is nothing else. On the left hand side, you have only x1 dot and x2 dot. There is nothing else. Okay, and you ended up with two differential equations, each of them first order, which means that the overall order of the system is 1 plus 1, 2. Okay, and since this guy is a nonlinear term, and it's the only term that's nonlinear in the dynamics of the system, it's going to make the whole dynamics of the system as a nonlinear dynamics. Okay, at this point, you might ask yourself why I'm doing this. Okay, I'll tell you guys this. First of all, this is much nicer than having a bunch of higher order derivatives in the dynamics of the system. This is much manageable. Okay, and also this is well suited for numerical calculations. Okay, you basically derive these equations, dump them in MATLAB, okay, and MATLAB will take care of all the numerical solutions for these differential equations. Okay,